So this segment will be about the Spotify search bar feature implemented inside the Spotify component of Home Assistant. In order to implement this feature, we have edited some files inside the Spotify directory, such as the mediaplayer.py, browsemedia.py, init.py, and we have added a file, the Spotify search card.js, inside a new directory inside the Spotify one, which is the UI directory. First, we have defined the async search media function, which is an extension of the abstract function defined by a media player inside Home Assistant. The goal of this function was to extend it to the Spotify search functionalities, so that this function handle all the searching part linking Home Assistant with the Spotify external library. The main issue with this function is that it requires in entry a search media query object and will return a search media object, which are both Home Assistant objects. However, the Spotify external libraries uses its own custom-made items. Therefore, we had to define a way to convert the items, the object, to a Home Assistant type and a Spotify external library type. So this function will convert the filters given in parameters in the query into a Spotify type, a Spotify external library type, before being used by the external library. Then the search is done, and the results are converted back into Home Assistant object before being stored inside a globally accessible dictionary, which is the item data from the Home Assistant class. Then we have defined the process search result function, which goes through every item in the result in order to convert them from a Spotify external library type into a browse media type used by Home Assistant, putting them back into a list that can be used by Home Assistant.
To conclude the backend part, we have the convert to browse media method. This helper function converts an item from Spotify data classes by calling the appropriate conversion function based on its type, and then it creates a browse media object from its attributes, browse media, which is the media data class used by Home Assistant. For displaying search results, we added a new value to the browse media enum and to the library map representing search results. This allows us to include a directory in the media player's card. We choose to use the directory types for its children because, unlike tracks or other media types, it can hold multiple different types of media, making it the most flexible options for search results. Another important point is the build item response method, which is responsible for opening any media or directory from the Spotify media player frontend. We've extended this method to handle our new directory type, and so when this directory is opened, the method retrieves the data stored during the search operation and adds all the corresponding items to the displayed list.
Inside the init.py file, we have added inside the async setup entry function a piece of code allowing us to generate a URL linking the UI directory to it in order for the Home Assistant instance to be able to find this directory and then load the custom-made JavaScript card to be loaded. Finally, we have coded a custom dashboard card for Home Assistant, mainly using the documentation about custom cards of the front-end part of Home Assistant. Inside this card, there's a function handling all the HTML part, therefore all the appearance the card will have. Then there's two functions, one allowing us to process the search, calling the defined function inside media player, and then one opening the results by opening a media browser directory. Finally, there's a function used by Home Assistant in order to define a custom menu in order to configure the card.
To test the search bar of Spotify, I needed to add test methods in testmediabrowser.py and testmediaplayer.py. To make the existing tests still viable, we also needed to change the snapshots to accommodate the search bar. To implement the test methods for the media player, we used the already existing Magicmox infrastructure and used patches with side effects to compare the return values of the search bar functions with what is expected. I also tried to think of things that could fail during a search, such as having an empty search, having unsupported items, and filters not actually filtering correctly. Since only a helper function was implemented in Spotify Browse Media, only one test was written for it. In the test method test async search media success, we are testing whether async search media converts the objects to browse media objects and doesn't lose or corrupt any information when given the correct parameters for all search types. These asserts can be seen here. Test method, we are testing the robustness by actively throwing an error and expecting async search media to return an empty list. In the method test process search result skips unsupported items, we are testing whether unsupported items get skipped correctly while still keeping the original order of the supported items. In the last Spotify Media Player test method, we are testing whether the filtering works for all different search types. We are also again testing whether the data is kept correct and in the right order, and asserts can be seen now. For the added functionality in a media browser regarding the search bar, we are only testing whether the method convert to browse media handles being passed an unknown media type correctly.
So I am gonna show you what I did for the audiobook support. My goal was to add another card in the browse media of Spotify to show the saved audiobooks. So everything is on this file, browsemedia.py. So what I did is that I added new cards, current user saved audiobook, and it's a browsable media, and the card is named audiobook. So I decided that the audiobook was the category was a directory of playlists. Audiobooks are playlists. A playlist filled with track, and the tracks are the chapter. I decided to take playlist and tracks because this does already exist, and I couldn't create a new media type named audiobook because if I had done that, I would have to get an icon to show them in the card, and it's front end, and I can't do it. So I already use type, and then to create my card, it's in this function here. So build item response. So when it's an audiobook, current used the received audiobook, I create for each audiobook, I add the ID of the audiobook, the name, and I specify that the type is media type audiobook as I show you. And so it creates the audiobook, and then I need to create the chapter of the audiobook. So when the type is I'm going to it. It's media type audiobook. Then I go through the chapter thanks to the external library, and I put like in playlist. I put all the chapter. I'm making sure that the title and the image of the playlist is the one of the audiobook, and that's pretty much all. The last thing I did is get chapter item payload. So I did this and it's there. So because everything has a get item payload, I did it for the chapter and it doesn't change anything. The only thing is just I putting media track. Media type dot track because as I said it is considered as a track, an audiobook, so it can be played easily by the media player.
So in this video we'll see the different tests written for the new audiobook support feature. Let's start with this. And so in this test I updated the Spotify library to now include audiobooks. So earlier it would return the categories only playlists, albums, artists and shows. Now the snapshot also includes an audiobook category. This will confirm that the media browser correctly recognizes the audiobooks as the part of user Spotify library. And next we have a test browsing updated version. So in this test we added new tuples. This is the audio book thing, and this means that the test will now cover browsing both the user's saved audiobook and an individual audiobook item. Then the code also calls this. So this is for simulating browsing into the audiobook, similar to like how one would explore a playlist. Then the snapshot comparison ensures the chapters and the metadata are correctly displayed. And we have this one. This is for checking if the user has no saved audiobooks. So after the same browse function, the test will assert the return structure matches an empty snapshot or not, meaning that the system doesn't throw an error and handles the empty state nicely. And yeah, so this is overall the new test to validate the audiobook functionality, and the test run.
In this video we'll see the forward and backward seek functions. So first we're registering the services here, and then writing the functions after the see function so that it maintains a continuity like that. And first the forward function. So this starts with the decorator, obviously async refresh after, which refreshes the media after execution. Inside it first checks if the self media position or self media duration are none. So if it is, it returns immediately to avoid running calculations without valid data. And then it calculates a new position using this min, which means it adds 10 seconds to the current position, but make sure it doesn't exceed the total song length. And then finally it calls the self coordinator to move the playback to the new position, converting the seconds to milliseconds for the Spotify API since it functions in milliseconds. And then the backward function. The backward function is kind of similar to the forward function. This one also uses async refresh after to refresh, and then it begins by checking the self media position. If it is none, it returns if no position data is available. Then it calculates the new playback time with the the max, subtracting 10 seconds from the current time, but ensuring it never goes below 0. The result is then converted to milliseconds, similar as the forward function. Thank you.
In this file, we are testing the implementation of the seek forward and seek backward functions that we have written in media player.py. We first will import the services from media player, and then there are 4 test cases that we're testing here. The first one is the normal forward, which usually checks the it simulates the current playback position and the track duration. Here it is at 50, and the total duration is a 120-second track. So once all this basic setup is complete, we'll trigger the service call, and after the user presses the skip forward button, so the position would move to 50. 60 from 50. That's like 10 seconds forward, and yeah, that's about this. And this is forward exceeding duration. This is an edge case when skipping forward would usually exceed the track duration. So here we are starting at 115 and the song ends at 120. So when we skip forward by 10, it shouldn't take us to 125, which so the code should instead stop right before the end. After the same integration setup and all the service calls, we check that the C commands stop at 119. And the next one is a normal back. Next we have test skip backward, which is testing for the normal backward skip case. Here we're like 8 seconds into the track. When we skip backward by 10 seconds, the new position should be negative, which isn't allowed. So when we call the service and the test finally asserts, this will confirm the backward skip works and doesn't go below 0. And the last is a classic the last edge case, which is the lower boundary logic holds even when we are very close to 0. We are like 5 seconds into the track. Skipping backward by 10 seconds would go negative, but again our code should clamp it at 0. We perform the async service, and this will return to 0, not -5 or something. And the tests successfully run.